Hello friends, welcome back for another deep learning project named Entity Recognition, where we will use a transformer to recognize the named entities from a sentence. And before discussing about the implementation of the named entity recognition using transformer, we will discuss on the transformers details and how we will use the data and how we will feed the data to the transformer. So for that we will move to notepad. Let's move to the notepad. Transformer is nothing but an architecture in deep learning which revolutionized natural language processing by replacing recurrent and convolutional architectures with a model built entirely on self-attention mechanisms. I hope you understood. Transformers are those architectures which completely based on self-attentions. Let me increase the font. Transformers. So what are transformers? Transformers are deep learning or artificial neural network architectures which depends solely on self attention mechanism. These transformers revolutionized the natural language processing by replacing CNN and RNN architectures. So that's what the transformer is. So we know RNN can remember the word orders and CNN also can remember the location of each word, which is specially identifiable for CNN. So for those cases we don't need positional embedding. It's an embedding which will be used for capturing the word order in sequential models and pixel order in vision models. So for the case of transformers, we will be using a position embedding layer. That's a sure. So we need a position embedding layer for remembering the word sequence order. Then let's discuss the architecture of transformers. First, we will have an embedding layer which does token embedding. So token embedding is nothing but tokens, that is words or subwords converted into vectors via an embedding layer. So what is this? Tokens, that is words or subwords converted to vectors via an embedding layer, which is called token embedding. And then we will have a position embedding. As I already told, we will have a position embedding because transformers don't have recurrence or convolutions. When we add this position embedding, we will capture the token order or sequence order or word order. So position embedding are fixed vectors which will be added to token embedding. You might be thinking, what is position embedding? So that is nothing but the indexes of the words from the vocabulary will be embedded and added to the token embeddings. These are fixed vectors or embeddings which are added to token embeddings. Then in third, we will have an encoder repeated n times, basically n equals to 6. Then we will have a decoder repeated n times. Then we will have an output layer, that is nothing but a dense layer. The transformers have the 4 steps of this architecture, and we are adding the output layer to the end so that we can recognize the named entities. Similarly, you can also do the parts of speech tagging through this approach, which we will apply for NER, named entity recognition. So here you might be thinking, what is the encoder and what is the decoder? So let's break down the architectures. Encoder is nothing but a number of layers which takes out the features using multi-head self-attention and feed-forward network along with residual connection. So encoder comprises of multi-head self-attention. This will allow each token to attend to all other tokens. That is what the pure greatness of transformers, that each token will be allowed to attend all other tokens. This multi-head self-attention will capture different relationships because the each token will attend to all other tokens. That's why this happens. So let's break down. The first one is allows each token to attend all other tokens. Then The second thing is captures different relationships between tokens. The first layer in encoder is multi-head self-attention. Then we will have a feed forward network, also called multi-layer perceptron. So feed forward network. So it's nothing but a simple two-layer multi-layer perceptron applied to each token. I hope you know about multi-layer perceptron, and multi-layer perceptron is nothing but two dense layers with some GALU activation or ReLU activation according to our needs. It is a simple two-layer multi-layer perceptron applied to each token. Then we will have residual connection and layer normalization so that we can stabilize and speed up our training. So what we will have? Residual connection and layer normalization, which will stabilize and speed up training. This is encoder architecture which will be repeated several times, generally n times. Then let's break down the decoder. In decoder we will have masked multi-head self-attention layer. This masked multi-head self-attention will prevent tokens from attending future tokens. Why we are doing this? Which will important for auto-regressive generation. I hope you are understanding. We will have a masked multi-head self-attention layer which prevents tokens from attending future tokens. So let's write that. We will have masked multi-head self-attention layer which prevents tokens from attending future tokens. Then we will have a multi-head attention layer which attends to encoder's output, helping the model relate input and output sequences. I repeat, we will have a multi-head attention layer which will attend to encoder's output, helping the model to relate input and output sequences. Multi-head attention which attends the encoder's output, which helps to the model to relate input and output sequences. Then we will have as usual a feed forward network and residual plus layer normalization, that is same as encoder. We will have feed forward network and we will have residual also layer normalization as in encoder. So this is what the architecture behind the decoder. Then we will have the output layer. The final output layer is passed through this dense layer. In output layer we will have a dense layer where we will use softmax function as activation function to generate predictions. In output layer we will have dense layer with softmax activation function. So this is the architecture of model. Let's discuss on how we should pre-process the data and how we should feed the data to the model. So in each example that we feed to the model, we will have two things. One is x, another one is y. The x is nothing but the sentence tokens or sequences. It's nothing but sequences or tokens or embeddings, while the y is also sequences, tokens or embeddings with special tokens like names of person, location and organization. So y is nothing but sequences or tokens or embeddings along with special tokens like names of person, organization, location, etc. So you might be confusing what are you speaking about. So let me give one example to clarify this thing. So let's think we have a sentence like India and Pakistan war will occur very soon. So in X we will have India and Pakistan war will occur very soon, and this. So this is our X. For this we will convert Y as this is a miscellaneous, as this is a country name, and for and we will have 0. For Pakistan we will have some miscellaneous value. For war we will have 0. For will 0. For occur 0. For very 0. For soon 0. For dot 0. This is Y, through which our model will learn this. So I hope you understood how we will feed the data and the architecture of our model. So let's move and implement Kaggle notebook and make sure that you are having accelerator GPU T4 times 2 and environment preference as pin to original environment. So we are using a dataset from the datasets. The dataset name is CONLL, kernel. So available the dataset in this library called datasets. For that, as we don't have that library in our Kaggle notebook, so I am installing it. And also let's download this dataset. So let's run to install. After doing that, we are importing the required libraries like OS, Keras, NumPy, Tensorflow, and the dataset that we are installing, and also collection and kernel valve, and also Keras hub. And from Keras we are importing operations layers. From dataset we are importing load dataset. From kernel eval we are importing evaluate. So let's run this cell and import all these required libraries. So you can see the requirement is satisfied. That means the datasets library is installed. After that, we have done a GPU connection so that we can use the GPU as the accelerator for training our models. For that, we have a method called mirrored strategy in the TensorFlow library in distribute module of that, and instantiating that in the strategy variable, so that using this strategy we can use the accelerator for training and increasing the speed of training. So let's run this and build the strategy. And also we are using num replicas in sync attribute with the strategy variable to get the number of cores. Let's run it. So you can see we have only 2 machines in the GPU system. Okay. After that, from kernel 2003, we are loading the data to the variable kernel data. So here you need to specify yes and enter, so that we can get train, validation and test splits. After this, let's see the kernel data. So it will return a dictionary. You can see this is a dictionary with train, validation and test 3 keys, and all 3 keys are also dictionaries. Which contains 2 more keys like features and number of rows. So in train dataset we have 14,041 rows. In validation dataset we have 3,250 rows, and in test dataset we have 3,453 rows. And we have features like ID, tokens, POS tags, chunk tags and NER tags. So as we need only name entity. That's why we are using NER tags only. We will remove POS tags and chunk tags. But if we want to do POS recognition or chunk recognition, we can use POS tags or chunk tags. So let's move forward. After that, we are taking out the NER tags and tokens and writing that to a file. So for that, I have written a function called export to file, where I am providing a path, export file path, and the data. So we are opening the file path in write mode as F. Then for each record in data we are iterating over. We are taking out the NER tags and tokens. So we are removing these POS tags, chunk tags and IDs. After that, if length of tokens is greater than 0, that means if we have some tokens, then we are writing to this file export file path, we are writing the length of token, then a slash t, then we are joining the tokens, then again a slash t, then we are joining NER tags. So that's what we are doing. So after that function, I have created a directory called data using the mkdir method applied to the OS library. Then we are providing a path and data for train file and providing a validation path and validation data to create a validation file. So let's run and create these two files. So successfully we have created the two files. After that, I have created a function called make tag lookup table. So this lookup table will give us the lookups of names like person, organization, location, and some miscellaneous like countries, rivers, etc. So here I have levels like IOB levels. IOB means inside, outside, and between. So in our case we will use only between and inside levels, and then we have NER levels like person, organization, LOC and miscellaneous. Then we are generating cross product between IOB levels and NER levels. With IOB levels and NER levels we are joining a hyphen between them. Then we are adding two more levels called pad and O. We are considering all levels with padding value and O value. Then we are creating a dictionary with keys as range of length of all values, and the values are the levels. So let's call this function and save that in mappings, and let's print the mapping so that you will understand it better. So here you can see the 0 key indicates pad, 1 indicates O, 2 indicates B person, 3 indicates B organization, 4 indicates B location, 5 indicates B miscellaneous, 6 indicates I person, 7 I organization, 8 I location, and 9 I miscellaneous. After that we are taking out all tokens from the trained data, then converting them to lowercase and making the list again for building a NumPy array. After that, we are counting each token using the counter method and saving the count values in counter variable, then printing the length of counter, so that from this we can assume what is our vocabulary size should be. The vocabulary means nothing but the words available in the corpus. The corpus is nothing but all the sentences available in the trained data. So we have the counter with counts, and we will print the length of counter, that means the length of vocabulary, and the number of tags is length of mapping, that is this is the number of tags, that is nothing but we have only 10 tags. Then we are taking vocab size 20,000. You can also take the vocab size to length of the counter, and let's generate the vocabulary. Here, applying the most common method, we are taking out 20,000 minus 2 because we need to have unknown token and we need to have mask token. Mask token is for masking zero values. Unknown token is for not considering the unknown values. So it will give us two values. One is token, another is count of the token. Then we will append only token to the list, and that will be our vocabulary. So with that vocabulary, we will train a lookup layer from Keras, that is string lookup, and save that lookup layer as lookup layer. Let's run this. It may take a few seconds. So here you can see we got the number of elements present in the counter is 21,009. That means we have 21,009 words as all tokens, but we are taking out only 19,998 most common words from the all counter values. After that, we will prepare and make dataset. So from the file, just we saved kernel_train.txt and kernel_val.txt. We will load as text line dataset and save that in train data and validation data respectively. So we have loaded. So let's see the text present in train data, that is what way we have saved, it will return the same way. So we will take one line from the train data. So let's run this. So here you can see it has returned a text, a tensor, where you see 9/t EU/t reject/t German/t call/t 2/t boycott/t British/t lump/t dot/t 3/t 0/t 7/t slash t 0 slash t 0 slash t 0 slash t 7 slash t 0 slash t 0 and save and dtype string. You can see this EU rejects German call to boycott British lamb, then dot. So EU is a country name, that's why we have 3 here. But rejects is a variable which is not a name, that's why we have 0. Then German is also a country name, that's why we have 7. Call to boycott. These are also not names, that's why we have 3 zeros. Then again we have British, which is a name, that's why we have 7. Then lamb and dot, these are not names, that's why we have 2 zeros. I hope you are understanding what I want to convey you. So after that, I have created a function called map record to training data. So when we provide the record like this, when we provide, it will split at slash t. So it will split at slash t and returns as the record. Then the first value, we know that the first value indicates the length of tokens, that is 9. That is the length of tokens. We are converting to number, so that from string it will convert to integer. From here to up to here we will have the tokens, and from there to here we will have tags. So that's what we have done here. From 1 to up to length plus 1 we will take out that as tokens. Then from length plus 1 to the last is our tags. Now as tags are in string format, we will convert them to numbers of integer type. Then we are adding 1 to each tag and returning back tokens and tags from the method. Let's run this. So the function is created successfully. So when we pass this to the function, we will get tokens and tags. And now tokens, for tokens we need to pre-process the tokens into vectors of integers. For that we are using the lookup layer. So at first, when we pass the tokens to the pre-process layer, it will lowercase all tokens, then pass that to the lookup layer and return as the vectors of strings. So let's create this function. After creating these two functions, we are applying map method to convert the record to training data. Then again we are applying a map method for pre-processing as per the requirement of our data. Then we have padded batch with batch size. This is used to get the padded batches. That means we will have the fixed length of each sequences. Let's run this. So after that we are coming to the transformer part. So here we will take first of all inputs where we don't know the batches size, and the d type should be int 32. Then we are using token and position embedding layer from Keras hub to get the embeddings, and this is the layer available in Keras hub which does the two functions. One is token embedding, another is position embedding. and this layer will take three things, specifically vocabulary size, sequence length, and embedding dimension. So the vocabulary size is the vocab size, that is 20,000. Sequence length is 128, and embedding dimension is 32. That means the outputs will be of dimension 32, and these embeddings will be provided to the transformer encoder. Here we are not using the transformer decoder, and we don't need that. That's why we are not using the transformer decoder. Here just we are using the transformer encoder. For that we have a layer in Keras hub, and it will take three arguments, namely intermediate dimension, that is the feed forward networks units, and number of heads, which is for multi-head self-attention, and the dropout. So we are dropping 10% from all outputs. So we are providing embeddings to this transformer encoder, which generates the self-attention with all tokens and returning back as X, and then we are dropping 10% from X. Then we have a dense layer with 32 units and ReLU activation. Then we have a dropout layer with 10% of dropping rate. Now finally we will have a output layer, a dense layer, where we are providing the units equals to number of tags and activation equals to soft max. So it will classify the names as, it will detect the names from the sentences, and let's return the model using the keras.model with inputs and outputs from the function build model. So we have defined a function for building the model. Now we are using a custom non-padding token loss because we have padded batches in our pre-processing of data. You can see we have padded batches. So for that we have added this custom loss. So in custom loss we are having a class with subclasses loss class, and we have a constructor method init with the name custom NER loss, and we are calling the constructor. After that we have a call method which takes two arguments, y true and y predicted. So our loss function is pass categorical cross entropy function, which will give us the loss, and we will take out the mask values, that if y true is greater than 0 we will get the mask and compute the mask with the loss, then return the total loss out of mask. So that's what the custom non-padding token loss will do. Let's run this. After this we will build and compile our model under the scope of strategy so that we can use the accelerator GPU for training this model. So we are using Adam optimizer and the custom non-padding token loss as the loss. Let's compile the model. The model is compiled successfully. Let's train our model with 10 epochs. So model train is started. After 10th epoch, we have training loss equals to 0.04 and validation loss equals to 0.25. So there is no greater impact in validation loss. You might change the number of epochs and other hyperparameters discussed above during model building. After that, we are building an inference model from the model just we built. So for that, we have defined a function inference model which takes a raw text, and then we will split the text and save that in tokens. Then we will reshape the tokens to this new shape, that is, we will make it a sequence. Then we will pre-process the tokens and get the vectors using the preprocessor we have defined above. Then we will use this pre-processed vector for predicting the named entities with predict method and set that in output. After that, we will take out the indices of the output through the argmax function of numpy and save that in prediction. And now we will do the mapping of that predictions and return the prediction. So let's define this function. Function is defined above. So we are taking a text like EU rejects German call to boycott British lamb. That's what we have discussed above. The same sentence we are using. Let's run this. So you can see EU returned BLOC, rejects as O, German as ILOC, call as 0, to as 0, boycott as 0, British as ILOC, lamb as O. So as this is the sentence already used in training, it returned all correct names. Let's change the text, that is India and Pakistan war is going on. Let's go for this text. So here you can see it is returning PER for India and IPER for Pakistan. That means it is considering that India and Pakistan are two names of persons, not locations. So thank you very much for listening me patiently. Have a great future and develop your own models like this. Thank you.